Hello students, welcome back to another lecture on classical mechanics. And in today's lecture number 20, we are going to see the special case of the Sun-Earth system. And in order to study the Sun-Earth system, we will consider a generic situation of a two-body problem, which means that we are going to consider two objects, and we are going to use the particle mechanics in the calculation, which means that we are not going to consider the moment of inertia and so on. Okay, because when the dynamics is taking place in the entire space, we can consider the sun as well as the earth to be particles of masses m1 and m2. So that could be the assumption that you can take. And in fact, if you are calculating the moment of inertia, for example, the spin of the earth itself could be a small number in comparison to the angular momentum, I mean the orbital angular momentum of the earth. So in comparison, their magnitudes are reasonably small, and therefore it is a good practice that not considering their moment of inertia does not affect the entire calculation. So therefore, let us start with what is meant by, in a generic situation, what do you mean by a two-body problem? Let us draw a diagram. And then for the purpose of calculations, we need the coordinate system, and therefore let us assume that the coordinate is located somewhere outside the two-body system. So it is located somewhere else, and therefore I am now drawing like this. You draw a line, okay, from the origin to the center of the mass. So let us draw first line like this. So that would be the line which will be the line joining the origin of the coordinate system to the first mass. And similarly, you repeat it once again and then take it to the center of the second mass. So in that case, we will be having like this. You draw the line joining their centers from here to here. And the distance of the first mass from the origin, so we will give the symbol R1. And then arrow is very important because it's a vector quantity. So all measurements are done from the origin of the coordinate system. So the arrow should be pointing towards the mass. And similarly, for the second situation, R2 will be the distance, corresponding distance. Now, we will be having only R1 and R2 with us. We have only that. But what is the distance between the two masses M1 and M2? We do not know, in the sense that we have to calculate. Okay, which means that let us represent it by another vector R, and let us give the symbol, let us give the appropriate arrow, which means that the distance from M1 to M2. The arrows are very important because they represent the vector quantities. I think you are following the white color cursor. Okay, so the white color cursor I am showing, right? So you start from the origin and then travel along the R1, and therefore the equation that you are going to write down will be like this. Then from M2, I will be traveling like this. So actually I will be traveling like this, and then I will be coming here. When I am coming here, I see that the arrow is opposite to me. So this is the direction of my travel. I am walking like this, but however the arrow is in the opposite direction, then therefore you put a minus. Then how much is the value? R2. So this R2. If I do that, and then I will be traveling like this, and ultimately I will reach my original place, my starting place. Since I am reaching the starting place, the total distance traveled by me is equal to 0, and that's all. And that is the triangle law. So once you write this particular equation, immediately you can see that the script R is given by R2. So you take this to the right side, and then I can write down that this is R1. So that means now it is very clear that the script R is going to depend on these two things, and therefore you don't require anything like R3. Now you understand that something like R3 is not at all required. That is what I tried to explain. So once this is clear now, that R1 is a vector, R2 is a vector, now we can write down the potential energy, kinetic energy. Thereby we can write down the Lagrangian. So that part we will do now. When you write down R here, the meaning is that it is the set of 3 points x, y, z in the space. And similarly, when we write down R1, so it is something like x1i plus y1j plus z1k in the ijk notation. And the point to be noted, I am emphasizing, is that when you have an R1 vector like this, there are 3 components are there. This point has to be remembered. So once this is clear, now we'll write down what is the kinetic energy. The kinetic energy of the two masses will be given by half m1 into. So as you see that this is an x1 dot square plus y1 dot square plus z1 dot square. Then you have the second mass, and therefore we can write down like this, m2 into, you repeat it for x2 dot square plus y2 dot square plus similarly z2 dot square. So that's the kinetic energy part. Later we will convert it into the spherical polar coordinate system. So to start with, it will be a good idea to start with Cartesian system, and then we can move along later. Then the potential energy is this is the place where we are going to make a possible realistic situation, namely the sun and the earth. If you are going to consider, okay, so this is how we are going to start with. Let us say that if you are going to have the plan to have the potential energy between the sun and the earth, or between any two planets for that matter, then you already know what kind of potential it is, and it is a gravitational potential, and therefore this will be like, so this symbol tilde is like, the potential energy is like minus g into gravitational constant into the mass of the larger object, the mass of the smaller object divided by the distance of the separation small r. So now you see the placement of the script r is very important. Okay, so now this expression has a script r. Script r means distance between the two masses, capital M and small m. That is very important. You can't use the normal r here. Okay, if you are going to write like g into m divided by something like r1 square, this is wrong. Similarly, if you are going to write, in case if you write like this, and this is also wrong, because the r1 and r2, they are two different vector quantities in our diagram. So the meaning of this equation should be clear, that it should be the distance between the two masses. So therefore that is looking like, so how is this exactly going to look like is, in our problem we have the mass of the first object, mass of the second object divided by the script r. Just now we have found out what is the script r, and that is actually r2 minus r1. That's what we are going to write. And then this being the square here, we are taking the modulus of the vector and then taking the square. So the potential energy appearance, or this is how the potential energy is going to appear, and the negative sign is only an indication that it's an attractive force is going on in the system. Okay, it's a stable system. That's what it is. But there is no compulsion that every system should be like that. But this is the most interesting situation where an attractive potential is there. And it is an interesting point that we will be dealing with this scenario. Okay, so yeah, there is a point to be noted. A small point to be noted is, yeah, so I have written square here. Square is the one corresponding to the, you know that the square corresponds to the force, so I have written force actually. So let me therefore remove this. I have written force, so that's the reason. So I have written the expression for force. Now we are talking about potential, so that square should not be there. So that is what I am making now. Yeah, so the potential energy is gmm by r. Okay, not a square. So if there is a square, then it means it is a force that we are talking about. Fine. So now what is the conclusion, or what is that I am interested to express to you is that this expression ultimately is, this particular expression depends on, or we say that the potential energy does not depend on, let me write down clearly, the potential energy does not depend on r1 vector. You can see, but it is r2 minus r1 is different. Okay, we cannot say that this is depending on r1. Okay, this expression doesn't depend on r1, and similarly also it doesn't depend on, okay, also not on r2. So this is the observation. Now say, only when you observe certain thing, your mind will think what to do next. Okay, that is why I'm explaining this. Now this expression, that is the minus gmm divided by the script r, doesn't depend on r1 and doesn't depend on r2, but rather what it depends on is but on the script r only. This is very important point, but on script r only. Now here, when I write the script r only, you have to again give additional importance to note that the script r means it is the modulus of the script r vector. So which means that, so this is another point, which means, so let me therefore write down that which means angle is not entering into picture. So these are the important observation. Only when you observe something, you can think about what can be done next. So this kind of information is going to be very crucial. In fact, it's very important. That's why I'm taking some time and explaining. The appearance gives you a lot of suggestion into the equation, and that gives you further conclusions. Okay, so the conclusion or the important observation from the equation, which equation is this one? I'm talking about this one. Okay, so the appearance is, it clearly tells you that the potential energy doesn't depend on the position vectors of the masses m1 and m2, but instead it depends only on the magnitude of the distance between. Magnitude is very important. The reason why it's very important is that one particular variable angle is not going to come in the equation, and from your Lagrangian mechanics or Hamiltonian mechanics, this point is very important, because whenever certain variable is not entering into the equation, then you know that there is a that particular object is a cyclic quantity or a cyclic variable, which means that ignorable variable that gives you one constant of the motion. So this is very important. Why we are so much emphasizing on that it is magnitude only, direction is not there, means direction is not there means angle is not there, which means theta or something phi will not be there. The moment one angle is missing, then the corresponding conjugate quantity will be a conserved quantity. So therefore, what is something interestingly happening is that without doing much of the mathematics, we are going to discover the constant of the motion for the problem. So this is the point to be noted before we proceed further. So this is a point number 1. So I'll write down that this is a important point number 1. So there is a second point that we can note down is the following. So the second point that you can note down is that if you are not interested to do only the gravitational masses like the sun and earth, if you're not, okay, I want to do something more general problem rather than confining to the study of the sun and earth system. If you are going to say like that, then the potential energy term has to be slightly modified. So that is the point to be noted, and I am writing it as a second point. So first of all, now the expression that we have is like this. We have negative value. The negative value, purpose of the negative value is that it is an attractive potential. Then we have the gravitational constant, mass m1, mass m2, divided by the script r without vector quantity. That means it's a scalar. That is what I mean to say. So this is what we have written as the potential energy. And if you're going to say that the potential energy is going to be represented by capital V, okay, usually capital V, it's a usual tradition, right? Either V is potential energy or we can also use capital U. So these are the standard symbols that traditionally we use in physics, depending on whichever is convenient, capital V or capital U. So now how are we going to write down this expression is that we are going to say that this particular function, this potential energy, is going to depend only on R. So which means that this is the meaning, and which once again I will write down that the potential energy is going to be the modulus of the R vector, because originally R itself is a vector quantity, and therefore we have to be careful in writing like this. Because in our diagram, so if you see the diagram, the script R is a vector quantity, so that you remember. So just now we have done that. So this one, so I am talking about this one. Script R is a vector quantity, and therefore since it is a vector quantity, you have to be specific about the scalar that we are going to consider. So therefore the potential energy is going to be a scalar only, is to be emphasized here. So this particular equation is what we are going to move to a general situation. So what is the general situation is, rather than saying that the capital V will be a function of 1 over R only, we will say that mathematically this quantity can go to a constant. So minus is minus 1, right? It's actually minus 1 into, that's the meaning. So minus 1 into G into M1 into M2. That is the meaning of this, which means that this is a number. Minus 1 is a constant. G is another constant. The mass of the two objects is not going to change. Okay, let us, if that is the assumption, then they are also constant. So what happens is all these constants are coming, and therefore I can in general write down that there's an alpha. Okay, instead of writing so many constants into the system, it would be better to represent alpha as a constant, and that constant can have a minus also and plus 1 also, whatever it is. So the most general situation is alpha. Then you have a divided by then you divided by, you can have R like this, or even if you are going to generalize more general situation, we can say that it is a function of R. It could be any function of R. So we are coming back to this general appearance. Mathematically, we write f of x is the function, right? So that is why we say that f of r will be the most general way to write. In particular, v of r is a good notation because v represents a potential. So the point that I would like to emphasize in the second one is that we are moving to a general situation. In what way it is general is that there is no compulsion to use a minus. That is one situation. The second situation is the power of r. Here, this arrow tells you that the power of r need not be exactly 1. So that is another situation. So I can therefore see, I will write down that this is something like a beta. Okay, so any constant, then you can have r to the power of beta, for example. If you do like this is the most general one. This is the most general. We say that it's a central potential. Okay, you can ask the question why the r to the power beta should be there in the denominator. Okay, so as you see, now there is no importance for the denominator or numerator. Why it is not important is you can once again rewrite this equation. You see, how do you rewrite this? Alpha into r to the power of minus beta. So r can come to the numerator, and beta is a number. It can be plus also, it can be minus also. So we don't now demand any positive value, negative value, etc. And therefore any function is allowed now, and this is why this kind of appearance is known as the most general central potential. The only reason for using the word central is because of the magnitude r. Okay, angle should not depend. If angle is going to enter, no. So this is very important. So that is why I've been telling that these are the 2 points that you'll have to remember. If your potential is going to depend on r and theta, then this is not a central potential. So this is the important point. Okay, sorry, potential, PO. Okay, so theta should not enter into picture. So only v of r should be there. That is what I mean to say, whether you are going to use the appropriate symbol. Okay, whether it is script or whatever it is, depending on the correct diagram, the appearance will be looking like v of r, or it is like f of r. Then if it is the case, we say that it is the central potential. So now you know the definition of a central potential, and you also know which is the most general way of writing central potential, and you also know which is a particular case for the Sun-Earth system. So this is the particular case, and this is the general case. General case means this one, either this or this, whatever it is. Here it doesn't matter, plus or minus. Okay, these are constants. Those constant itself can have a negative and positive value. So it is something like constant into r to the power another constant. So this is the general introduction. I mean, what is that we are trying to do? And this particular potential energy is what we are going to substitute in our equation. Now, what equation we have is that we are interested to write down the Lagrangian, and for the Lagrangian, kinetic energy is available. Now, the question came here, for the Lagrangian, we should also write down the potential energy. So what should I write for the potential energy? That was the question that we are interested in. And the answer now we got, that the answer is that you can always write down typically alpha divided by r to the power beta, or any function v of r we can write down. So because instead of saying f of r, we can always say that it is v of r to only emphasize that v is a potential energy. That's all about it. So if you write like this, this is the most general potential. And if you are going to choose a specific potential of minus gmm, then we are going to the sun and the earth system, or in general any planetary system. That is the meaning. So let us now therefore coming to the our original discussion of writing down the Lagrangian of the system. Now the Lagrangian of the system is like this, that I have half into m into, now you have x1 dot square, x2 dot square, etc. So let me therefore write down in the compact notation, namely r1 dot r1, because now you understand what is r1. R1 means x1 comma y1 comma z1. That's a vector quantity. Then you take the self dot product to bring the half mv1 square, isn't it? And therefore, because these are velocities, you need to have time derivatives. So I am writing r1 dot. So that will be little bit compact notation rather than writing x1 dot square plus y1 dot square plus z1 dot square. That will be a little more lengthy expression. So this is for the first mass, therefore I will write down that this is m1, and then the similar expression you repeat now. It tells you that this is going to be, this is r2 dot, then dot, once again r2 time derivative. So that is the kinetic energy part. Then you have a minus the potential energy part. What we will do is we will simply write down that this is V of r. So this is where the placement of the potential energy is going to come, and this V of r is can take any value depending on the given problem. It can be the gravitational problem, or it can be an arbitrary problem. Arbitrary problem means what I mean to say is that there may be certain problems that may not be physical in nature. For example, we can generate mathematical problems, okay, just for exercise. It may not be representing a realistic situation. So you can generally create something. I can always write down 1 divided by r to the power of 5, f of r. So this kind of potential I can say. You may not have any realistic situation where a physics is taking place with 1 divided by r to the power 5 power law. This is called power law. Okay, whereas in the case of the gravitational case, how do you write the gravitational case is minus gm small m divided by, you say r. Now what is this power law? This is also power law where power is equal to 1. So now you know that this is power. This is also power law. So what I mean to say is that by writing down this V of r here, we can now discuss a more general variety of mathematical problems that may not necessarily represent physical situation. You can always discuss physical situation, that is fine. But if you want to go away from physical system and then only for the mathematical interest, okay, if you want to study some arbitrary potentials, then writing down this V of r is a good way to start with. So that is the reason why I have given the explanation. And whenever you want, the value of the potential can be substituted and then simplified, in which case we say that we are studying a particular system. I'll give you another example. Another example of the potential could be say half k into r square. So half k into r square is, what is half kx square? This is a force law that corresponds to, and you know that it's a kind of a spring constant. If you have k, then this is going to represent the potential energy of a spring. So therefore 1 by 2 is a constant, k is a constant, so all these things will go into alpha, alpha. Then you have an r to the power of 2, so this 2 will be equal to beta. So as I already told you, alpha into r to the power of beta you can write down in this form. If you write down, you can bring any potential, not necessarily gravitational. Okay, in general you can bring any potential, though this is a realistic potential, by the way. And fictitious potentials or non-realistic potential you can bring like r to the power minus 5 potential can be also studied. We can also study for mathematical interest. So the purpose is now clear. We have a two-body problem, and then the interaction between the two objects is a central potential. Okay, it could be any central potential that we are going to assume or we are going to consider. In that case, the Lagrangian is going to be written down like this. So this is the first starting point. So first of all, the starting point should be clear to you, and then we can ask the question, what is the way in which we can solve the problem? Okay, so let us think about the solution to this problem, or next what can be done. So we'll see that. Okay, so let me write down this expression in the what do you call the spherical polar coordinate system. We can write down like this: half into we can write down m1, so we can write down like this, r1 dot square. Now you know that these two vector quantities are taking a scalar dot product here, and therefore this can be written down like this: plus half into m2 into r2 dot square, and minus the potential energy of interaction. And here you have to be careful that we don't write r1, we also don't write r2, but instead we write the script r, and all the reason you know already. So this is ultimately this is the Lagrangian for the two body system. Okay, two body problem. I would like to specify clearly that it's a two body problem under the influence of, that is important, so under the influence of the central potential. Now, once we have we have done up to this, now we can think about how to proceed further. Now, before we proceed further, we think about what are the degrees of freedom of the system. Okay. Now, since you have two of the objects here, you need 3 degrees of freedom for the first mass. You know already, right? x1, y1, z1. That is required. Then you need 3 degrees of freedom to study the the position of the second mass. So 3 plus 3 are required. And then there is an interaction potential. Of course, interaction potential is going to depend on only the distance between them. So once you have 3 numbers here and once you have 3 numbers here, then this scriptor can be easily evaluated. You already know what it is. Of course, just to start with, I will write down x1 minus x2 whole square plus etc. So use this formula and then you can calculate this. So this gives you a general suggestion that there is the problem is actually 6 degrees of freedom. Which means, you know what do you mean by that? You will have to write down that many number of equations of motion, and therefore it is going to be fairly difficult problem. So that is how it starts with. So therefore what happens is you think whether anything can be done to the coordinate system in such a way that the number of degrees of freedom can be reduced. You already know what is the procedure in general. Whenever you start with a mechanics problem, we always want to know what is the minimum number of degrees of freedom that a system can have or can be reduced. We don't want to deal with maximum number of degrees of freedom. We always want to minimize this. Okay, minimization can be done in 2 possible ways. One is that if you have a constraint, then straight away the constraint equation will reduce it. If you don't have a constraint, then what is the possible mechanism by which you can reduce the number of degrees of freedom is that you have to change the coordinate system. Changing the coordinate system means you can either rotate the coordinates or you can move the coordinate. That is called a translation operation. You can translate the coordinates from one place to the other, or you can rotate the coordinates, or you can perform a combination of this, translation plus rotation. These are the options. Or if this is also not working, you can think about making a Cartesian to the polar, or you can convert Cartesian to the spherical. All possible things. These are the ways in which you can make the coordinate transformation. Okay, translation of the same coordinates, rotation of the same coordinate, or totally transforming the coordinate to a spherical system or something like that. So all possible ways that you are going to think. By doing this kind of transformation of the coordinates, is it possible to reduce the 6 degree of freedom problem to a smaller number? Okay, if I am going to reduce it to 4 degrees of freedom problem, then I'll be happy, right? 2 of them I'm reducing it. So that is the idea. First question is, will it work or not? That we do not know. That is the thing. So the idea is that if we are interested to do some kind of a coordinate transformation, and the purpose of doing such a coordinate transformation is that I am expecting in future that the degrees of freedom may reduce. If it is not reducing, well, all the work that you have done goes waste. All the work that you do is wasted, and then you will be returning back to the 6 degrees of freedom problem. So that is the idea. But first you have an idea, right, what to do. So now the statement is explained now. Our purpose is, let us try and see if you are going to take a different coordinate system, how many number of degrees of freedom is going to emerge. That is the idea. So for that, what we will do is, once we talk about the coordinate system, we need to have the visualization, and therefore I'm coming back to the original diagram here. And now you ask the question, fine, now that you have the 2 of the masses that you have, whenever you have several mass, you know the concept of the center of mass. Okay, center of mass means what? It is the location means position. It is the position where the sum of the all masses are present. That is the mathematical location. Okay, not physical location. You know what is the center of mass concept? Center of mass is it is the location where all the masses, that is generally we say that the total mass is concentrated at that point. Okay, so it's a mathematical concept clearly. Okay, so in that particular case, you can ask the question where the center of mass can be there, and your experience or your knowledge about the center of mass will clearly tell you that the center of mass will be lying on the line joining the 2 masses, and it can be located somewhere here. Maybe I'll put a dot here. So that could be a possible location. I'm not saying exactly. Certainly the center of mass is going to lie in between M1 and M2. That much is sure. Second point is center of mass will come to exactly middle place. Middle place if and only if two masses are equal. That also you know. If two masses are equal, then the center point will be the center of mass. But however, we know that M1 is a larger mass. Okay, schematically, M1 is a larger mass and M2 is a smaller mass. In that situation, the center of mass is going to be towards the larger mass, and therefore I have put the dot here. So I am now going to say that this particular point is going to represent the center of mass, COM. So if it is the case, the next one what we can do is that we can once again draw the coordinates and then show what is the corresponding variable. So that I will show now. So let me draw a line now from the origin. So what is the diagram that I am going to draw is from the origin you start and then come to the center of mass. So that is the place where center of mass. I have drawn a pink color line, and then once you have drawn this, now you can now put the arrow as usual like this, and then we will give a name. It has to be a different name, and therefore I will put a capital R. So capital R is the symbol that I am going to use to denote the location of the center of mass of the two masses M1 and M2. That's all about it. Now once you finish this, what is the meaning, or physically now you can understand after doing this, you will be in a position to at least understand what is going to happen. So if you are going to locate the center of mass is given by the capital R, then our conclusion, or what is the meaning implied by that, is that this particular object is going to remove. Remove means we no longer want. That's what we mean to say. It's going to remove R1 and R2. So that is the meaning. So either you deal with the position of the two of the masses, or you deal with the center of mass alone and forget about where are the individual masses. That is a concept. That's a fundamental concept of center of mass, right? So therefore, the moment you are going to put the center of mass location, which means that we are going to do away with. We are going to do away with means we no longer need them. That's the meaning. We no longer need this particular R2 and that particular R1. We don't want both of them. But instead, we will trace. Trace means follow. We will follow the dynamics of the center of mass. We will not worry about where are the masses located. Instead, we will follow where is the center of mass moving. That's the idea. So that means the dynamics of the center of mass will be studied instead of the dynamics of the masses themselves. That is the physical meaning ultimately it comes to. And therefore what happens is now we have to write down an appropriate equation from this particular diagram. So now the question is, how are you going to write the equation? Okay, that is the point to be noted. And therefore for that purpose you need to write down the general equation for the center of mass from your basic mechanics course. Okay, so that means I can write down like this. It is mass 1, okay, plus R1 plus. This equation is something which is there all the way from school, maybe in BSc. It is the basic definition for the center of mass. So there is nothing new here. So the center of mass of the two mass system is defined as this equation. That's why I am writing like this. There is nothing new. This is given by the center of mass. So this is the basic definition of the center. COM means center of mass. You have to be careful. Up to last class, we used to write COM for the constants of the motion. Okay. So now in today's class, COM means center of mass. So don't get confused. Constant of the motion is also there. We will write down that whenever it is coming. Right now, COM means it is the center of mass. So therefore, this equation clearly gives you how to calculate the center of mass, or the moment you know R1 and R2, how to find out the R. This is what I mean to say. Now it is clear. Now removing R1 and R2. What is the meaning of removing? Means if R is known to you, we don't want R1 and R2. That is the meaning. If you have all the three, then it is just extra information. We don't want extra information, right? We need only the minimum number of variables to specify the dynamics. minimum number. That is called degrees of freedom. If you have a lot of variables, then that is not degrees of freedom. So either you keep R, capital R, you keep capital R and throw the R1 and R2. That is option 1. Option 2 is you throw the capital R and keep only R1 and R2. Both are fine. Both of them are fine. But if both of them are fine, now the question comes, then why are you doing this work? So the answer is this. The answer is this. If you are going to have R1, I need 3 degrees of freedom, x1, y1, z1. If I have R2, I need 3 more degrees of freedom, x2, y2, z3. So how much is the total? That gives you 6 degrees of freedom. Now, suppose if I am going to use the center of mass, this is a vector quantity, and therefore it will have xi, yj plus zk. I will be having 3 degrees of freedom. So that gives you 3 degrees of freedom. So I will be using this capital R and throw this small r1 and r2. This option will give you 3 degrees of freedom. So this is one option for you, right? So you have to understand what is the meaning of the tick that I am keeping and what is the meaning of the cross mark. Tick means I am going to use the capital R, and I no longer want this small r1 and r2. If it is the case, my total number of degrees of freedom is 3. What is the opposite situation? Alternate situation. The alternate situation is, till now we have been discussing, is the other way. Okay, either this way, or alternate situation is use R1, R2, and we don't want capital R. So just reject the option for the center of mass. If you are going to do this, R1 and R2 will give you 6 degrees of freedom. This one I am going to reject. That rejection will give you 3 degrees of freedom. So finally, how many degrees of freedom are you going to work? 6 of them I have to work. So now the question is now clear. Are you going to do your calculation with 6 degrees of freedom, or are you planning to use 3 degrees of freedom? So that is the question, and the answer is straightforward, that we always want a small number of degrees of freedom. And therefore now you come to a general statement or general agreement that using the center of mass coordinate system is going to help you reduce the number of degrees of freedom. That means, what is the meaning is, that means the mathematical complexity means the number of equations you are going to deal with, etc., is going to be reduced a lot, and therefore solving the corresponding mathematics for the center of mass problem is going to be much simpler than when you use the original problem with R1 and R2. That is the conclusion. So our conclusion is clear. You have a solid reason why you have to study the center of mass coordinate system. It's a solid reason, and for this purpose, now we are making a clear conclusion that we are going to use the center of mass coordinate system. If it is the case, then the question comes, okay, we are going to use the center of mass coordinate system, then we have to use this equation. Now the question is, how are you going to use this definition for the center of mass? Namely, I am putting a box here. How are you going to make a combination of the center of mass equation, namely this one, and the Lagrangian? Because Lagrangian is something that you have already written, so you don't have to worry. It is already there. I will show that. This is the Lagrangian. So you have the Lagrangian here. You have to now combine this Lagrangian and the center of mass equation that you have there. If you combine them, then what is the conclusion? Then what happens is that the number of degrees of freedom is going to come down. That is the conclusion. How it is going to come down? For that you have to do some mathematical steps that you have to do. Okay, so that we will do in the next class.